This lecture is going to introduce linear regression, which is really the first method that we're going to study in supervised learning. So let's just start out with what regression does. So what regression is going to do is allow us to quantify the relationship between some outcome that we care about. Now that outcome is often called a response variable. Sometimes I'll call it a dependent variable. At times it'll be called the criterion variable. When we get to machine learning, it's called an output. Okay, so this is some outcome that we care about. We want to see how that relates to other factors. All right, and these other factors are going to be called predictor variables. I might call them independent variables. I might call them covariates. So the response variable or the dependent variable is always y. The independent variable or variables will always be x. One other term that you're going to need to know about predictor variables. There's two types of predictor variables, and these two types are factors and covariates. So factors usually refer to categorical variables. Now the term factor has other meanings in statistics and machine learning, but in a regression context, it's going to mean a categorical predictor variable, while covariates will usually refer to numerical variables. All right, so that's the basic objective of regression. Now, why are we doing this? Well, there are two main reasons, prediction and interpretation. So this will become clearer once we do more examples, and I promise to keep referring back to this. With prediction, we primarily care about predicting, the value of the dependent variable. So in a few minutes, we're going to talk about relating the maintenance cost of a machine to its age. So if all I care about is predicting how much it's going to cost me to maintain a machine, that's a prediction problem. The other reason why we do regression is to interpret individual effects. So we may want to know, as the machine gets older, how does the maintenance cost increase or change? Okay, so what we're really looking at when we interpret effects are slopes. Okay, so this will become clear once we get into some examples. All right, so what exactly is regression doing? Well, regression is it's really nothing more than a fancy way of computing means. So let me explain that statement a little bit further. What regression really does is it estimates a conditional expectation. It says, for a given value of x, find the mean of y. All right, so here's a little example where we're relating sales to advertising. So what regression simply seeks is, for a given level of advertising, let's say I set my advertising at 0.4, where is the mean of the dependent variable y, or in this case sales? And it's probably about here. If I have a higher level of advertising, where is the mean sales? It's about here. Right? So all we're trying to do is find the mean of the dependent variable, conditional and the independent variable. So if you think about it, there's nothing that new about this. This is what we've been doing with t-apply. So we were finding the mean of some variable based on some categorical variable. The only difference here is that rather than a categorical variable, we have a numerical variable such as advertising. Now let's talk about the linear regression model. So this is the linear regression model. For now, we're going to assume that we only have one predictor variable. And whenever we have one predictor variable, we're going to call this a simple linear regression. All right, so simple linear regression assumes that the data were generated according to this recipe. Okay, so all my y's are going to be some line. So this line is alpha plus beta x. That's often called the systematic component. So the systematic component is a line, and then we have some errors, and that's the random component. Now let me go show you a picture that illustrates what's going on here. So in this picture, what you'll see is that, here's our equation. The recipe that generated all of these points is that there is a line. So here is the line alpha, so alpha is our intercept, plus beta times x. So you'll note that I've indicated that slope as follows. Whenever you have a run of 1, the rise is beta. Okay, so every y is equal to some point on the line, and then we have this error. Okay, so the error, let's just say that our x were 4. Okay, the x is 4, then a point like this point right here is just that point in the line minus some error. So the error is negative in this case. Now we're going to assume that these errors have normal distributions. Okay, so the mean of y for a given x is going to have a normal distribution. So what we're really saying then is the mean of y follows this line, but then there's some noise that is not part of this general trend, that the mean of y depends on that line. All right, so with that picture in mind, let's just go back and go through a few more of these symbols. So what this is a very important relationship, and it just says that the mean of y for given x is that line, and then we've got the errors, and the errors have mean 0. They have some standard deviation, which we're going to call sigma sub e. Notice that the sigma sub e is constant across all these normal distributions, so that doesn't change depending on x. Okay, so if x is high, the standard deviation is the same as if x is low. These sigma sub e's, sigma sub e is called the standard deviation of the error. Often we'll talk about the error variance. So if you square a sigma sub e, it's called the error variance instead of the standard deviation of the error. So that's the basic model. Here's an example scatter plot where you do not have this constant variance. So remember what I said here. These normal distributions all share a common standard deviation. It doesn't change where, depending on x. All right. Sometimes you're going to run into situations where that assumption is not true. So here's a situation where notice the spread around the line is very small, but as x increases, the spread also increases. Or you could also say as the mean of sales increases, the spread around that mean increases. Whenever you have this situation, it's called heteroscedastic error variance. So this would be homoscedastic. Homo meaning the same, scedastic means spread in Greek. So here we have homoscedastic. This is heteroscedastic since the spread changes. Now this is going to be a problematic situation for us, and we will learn how to address this in a future lecture. We're going to see that we have to transform the dependent variable to get rid of this heteroscedasticity. Few terms. So I already said that whenever you have 1x, you have simple linear regression. Whenever you have more than 1x, we call this multiple linear regression. Now the term linear in both of these terms, simple linear regression, multiple linear regression, refers to the fact that the set of means of y, or means of sales in this case, have a linear relationship with advertising. So these means follow a linear path. Nonlinear regression is going to refer to situations where those means follow a nonlinear path. All right. We now have some understanding of the basic regression model. In real life, we don't know the slope and the intercept, and we have to estimate them from data. So let's talk a little bit about how we estimate those from data. So in practice, we don't know alpha, beta, and sigma sub e. So those are really the three parameters that are part of this model. So we're going to estimate these with statistics a, b, and s sub e. So just as we estimate the parameter mu with x bar, we're going to estimate beta with b. Right, so these are more examples of parameters and statistics like we talked about last time. So another term, I said that the mean of y for a given x, so that's mu sub y given x, let me refer you back, that was this equation. The mean of y for a given x is the point on the line. All right, so from now on, we're going to denote that point on the line by y hat. So y hat is going to be the point on the estimated line. And this is really an important concept. It's so important that we have a couple terms for it. So we'll either call these y hats, or we'll call them fitted values, or sometimes predicted values. So let me now draw a little picture of this for you. I've already sketched something out, and let's just say that we observe these points. And now, so I've just added a line that went through those points. So let's say that this is our regression line, and I'll maybe label a few points. This point where the line crosses the y-axis is going to be A, and the slope of this line, I'll again denote that by a run of 1 and a rise of b. So the equation of this line is y hat equal to a plus bx. Now, we've observed the red points, and these red points are called observations or observed values. The black points are the points on the line, all right? So these points are y hats. That is a y hat, whereas the red points are the y's. So it's really important to keep those two terms straight. So now let's go back to the course packet for a second. The next term that we need to understand is residual. So residual is the difference between the y's and the y hats. We're going to call these residuals e hats. So if we go back to my diagram, the black lines are my e hats. So the length of this line is e hat. Maybe I'll just draw a little bracket here to indicate that. All right, so if we take y, the red point, less the y hat, we get an e hat. In this case, e hat is negative. Over here, e hat is going to be positive. So let's draw that e hat as well. Kind of hard to draw with this writing pad. So that's an e hat as well. So these e hats are called the residuals. Now, the question is, how do we choose the line? So the answer to that question is that we want to choose the line that minimizes the sum of squared residuals. So we want to make the sum of these squared e hat values as small as possible. So this line that I threw up on the scatter plot is a pretty good line, and that's probably the line that minimizes those black residuals. Just for the sake of illustration, I'm going to draw another line on top of this, and this is meant to be a very bad line. Now the question is, what makes this a bad line, whereas the black line is a good line? The answer is that if you look at the residuals from the green line, the residuals would be very long. All right, so I'm trying to show the distance between the red points and the green line, and you'll see that the green these green residuals are much bigger than the black residuals. Therefore, the black line is preferred. So this is the objective function, and we would have to minimize this. We could do so with calculus. So if we were to differentiate this with respect to A, take the partial derivative of SSE with respect to A, then do it with respect to B, set those equal to 0 and solve them, you'll get the equations that give you the slope and the intercept. Now, I'm not going to do that. I'm going to show you an alternative way to derive this on a couple slides, which is equivalent to the calculus that I've just described, but a little bit more straightforward. Anyway, theorem, here's how we get the estimates. So the slope is just going to be the correlation coefficient divided by the ratio of the standard deviations. The regression line always passes through the point of means. So it's going to pass through x bar and y bar. So you have a point on a line. If you know the slope, you can determine the intercept then. One more result. We need to estimate sigma sub e. So what was sigma sub e? Well, remember, sigma sub e is the standard deviation of these deviations from the line. So we can estimate sigma sub e using the sum of squared errors. So remember, variances are just the sum of squared errors divided by the sample size. So we'll do roughly that. And we're going to divide by n minus 2 instead of n minus 1 because we've got two parameters in this model that we have to account for, A and B. So turns out that this will give us an unbiased estimate of the error variance. The square of this will be an unbiased estimate of the error variance. You can do some algebra and show that this is equivalent to this expression involving the correlation. This is a very important quantity. It will appear in all regression output. Unfortunately, different output will call it different things. So sometimes it'll be called the standard error of the estimate. Sometimes it'll be called root mean squared error. Sometimes it'll be called the residual error. This slide gives us some results that we're going to need in order to do statistical inference on regression. So by that, I mean we're going to want to compute confidence intervals for our slopes and intercepts, and we may wish to do some hypothesis testing on them as well. So this first result shows us how we can find the standard errors. So the standard errors, again, quantify how much these estimates are going to vary across samples. So small standard errors means very reliable. Large standard errors means less reliable. Another result is that these least squares estimates are unbiased. So across all possible samples, on the average, our B, our slope, our estimated slope, is equal to the true slope, beta. This is analogous to the result that we had before, where on the average we get the truth. So across all sample means, the mean of x bar, the mean of the sampling distribution, is equal to mu. Same is true for our intercept. Both A and B are going to have t-distributions. Now these t-distributions are approximately normal when n is fairly large. So we're going to be using t and z distributions to find confidence intervals and do statistical inference. So the last result that is on the slide is r squared. So r squared is also known as the coefficient of determination. R squared just is a measure of fit. It's a measure from 0 to 1. The value 1 means that you've explained all the variation in y using your x variable. So if we go over to my sketch pad for a second, if we had a situation like this, where all the points fell exactly on the line. So we explain all the variation in my y using this x, therefore r squared is 1. If you had a situation like this, where the line doesn't explain anything, that's an r squared of 0. So again, r squared describes the quality of the fit on a scale between 0 and 1, 1 being explaining 100%, 0 explaining nothing.